Alright, so that's one example. We wrote an algorithm for searching an array for a given number. We looked at the total running time, and then we looked at proving that the total running time was big O of n. Let's do the same thing for another example here. Let's search two separate arrays sequentially for a given number. So what I mean by sequentially here is we're going to search array 1 and then we'll search array 2, but we're basically doing the same thing. We're going to do loop through each of those arrays and look for a given number. So we have our function, and let's call it find num in 2, meaning in 2 different arrays. And we're going to pass in array 1, array 2, and the number we're looking for. Okay, well, how do we search two separate arrays for our number? You could write out two separate loops, but I'm going to take a shortcut here. And I'll just say we're going to return, and this function is going to do similar to what we did in the previous function, which is just return true if we find it. So we'll just return what we get from find num when we search array 1 for num, or if we search array 2 for num. So that's what this function is going to do. It's going to search array 1 for num, search array 2 for num, and we'll just use our find num function that we had before. Alright, so what is our total running time for this find num in 2 function? Well, we need to think about a couple of things here. First is, what is n? Is it sort of the length of array 1 plus the length of array 2? I think something that makes more sense for n is we can just say, like, notationally, n is going to be the max of array 1 dot length and array 2 dot length. Since we're using our find num function, and we already know the total running time of that function, if we say that n is just the max of these two things, well, we can say, well, we're doing 2n plus 1 amount of work for our first call, plus 2n plus 1 amount of work for our second call, and we'll have an additional plus 1 or plus 2, depending on how you want to handle the or here and the return statement here. So let's just say we have plus 1 for the or and another plus 1 for the return statement. I think I ended up with 3 plus 1s there. The number of plus 1s that you'll end up with doesn't matter that much. So just to be consistent with what I have on the previous slide, we'll say that the total running time of this algorithm is going to be 4n, so 2n plus 2n is 4n, plus 3. So we get 1 from the first find num, 2 from the second find num, and 3 for the return statement. And I think when I was doing these slides before, I sort of neglected the or here. Okay, so asymptotically, what is the running time of our new function? Well, asymptotically, we're going to do something similar to what we did last time, which is we're going to make a guess to start with. And you don't always make a guess. This is something we'll come back to, but for these simple examples, it makes sense to just say, well, we think that the total running time here of 4n plus 3 is linear. We're running through a loop twice, so it's like doing a linear amount of work twice. So 2 times linear is still linear. So we're going to just start by saying that. We think t of n is big O of n. Alright, well, what does that really mean? It means that 4n plus 3 is less than or equal to some constant times n for all values of n greater than or equal to n naught. And what do we have to find? We have to find a value for c and a value for n naught that makes this inequality hold, makes this inequality true. So I'll do what I did last time, which is sort of have this intermediate step. You don't have to do it this way. We'll look at another way to do it in a couple more examples down the line. But I always find it easier just to say 4n plus 3 is less than or equal to 4n plus 3n, which is less than or equal to c times n for all values of n greater than or equal to n naught. Okay, so what we originally had was 4n plus 3 was less than cn. That's what we wanted to do. And I'm just going to do it through an intermediate step here, whereby we first prove this. We first say that 4n plus 3 is less than 4n plus 3n, and then afterwards we do 4n plus 3n is less than or equal to cn. So if we know 4n plus 3 is less than 4n plus 3n, and we know 4n plus 3n is less than cn, less than or equal to, then we know that 4n plus 3 is less than or equal to cn. Alright, so that's me repeating the same things quite a few times, but sometimes I was emphasizing the n here and sometimes not. Okay, so let's do the first part. How do we get 4n plus 3 to be less than or equal to 4n plus 3n? Well, we can subtract a 4n from both sides, so we're going to have that 3 is less than or equal to 3n. Well, under what circumstances is some constant 3 less than 3n? Well, that's only true if n is greater than or equal to 1. Alright, so let's just hold on to that. We know that we're going to need n to be greater than or equal to 1. So we've done the first step. So you can say that this is step 1. Now we need to do our second step, which is to say that 4n plus 3n is less than or equal to c times n. And don't forget, we still have our condition here for n greater than or equal to n naught. So 4n plus 3n is 7n, is less than or equal to cn. Divide both sides by n, and we've got that c is 7. This is also conditioned on n being greater than or equal to 1. So n is greater than or equal to, well, it has to be 1, so n naught we might as well use as 1, stated as 1. So there's our proof. We know that 4n plus 3 is big O of n because we found a constant c equals 7 and a constant n naught equals 1 that satisfies the inequality.